Good afternoon, everyone. First, apologize for this delay. I hope it didn't cause you too much trouble. But now we are here. So welcome, everyone. Today, we'll dive in the world of photonic design. But first, just a very short introduction in case you don't know me yet. My name is Lisa Sitar. I'm a marketing officer at Infinite Simulation Systems and a moderator of this event. Before we officially start, just wrong screen, very short instructions on the tool you're currently using. So just letting you know that you have different options. Bottom left, you can react during the session. Top right, you have two important buttons. One is the setting button and the other one is the question tab. Here, one important remark that you cannot unmute yourself during the webinar. So if you have a question, and you're very, very welcome to ask questions, just please write it down under the question tab that you see on your screen, and all the answers will be provided after the webinar. Another thing, the webinar is being recorded, and you will receive this recording, including the presentation slides afterwards. So that's all about the tool. Today, I'm joined by my colleague, application engineer Ekim, who will tell you more about how to use Ansys simulation tools to tackle the growing complexity of photonic integrated circuits. So, Ekim, I will give you my word.
Hi everybody, and to those who I have already seen, welcome back. My name is Ekim. I'm the optical application engineer at Infinite, which means I work with the optical software of Ansys. And today I'm going to show you one of our software, Lumerical. So let's go. Let's continue. You already know that optics and photonics are all around you: cameras, telescopes, biosensors, lasers, and so on. The list is very big. I will not name them all, of course. And in order to design all those devices, Ansys has three softwares. We have already seen Zemax and Spios. And today we are going to look at Lumerical. Lumerical simulates the propagation of light through micro and nanostructures. So when the wavelength is about the same size as the structure itself, then we need to treat it as a wave, and we cannot do ray tracing anymore. So yeah, let me show you some examples of photonics. You can think of photonic integrated circuits, biosensors. In biosensors, there are often these small photonic components. In displays, you have very small pixels. Those can be designed and optimized using Lumerical. And you can think of gratings in LiDARs and in AR or VR glasses, and also so waveguides. So optical fibers are also an example of photonics. I said I'm going to show Lumerical, but actually Lumerical is not one software. It comes in many different flavors. So what I'm first going to do is I'm going to show you some of those different modules in Lumerical, what you can do with it. And then at the end, I will show you an example, so an example project. So let's go on. First of all, FTTT. FTTD stands for finite difference time domain method, and this is the Maxwell equation solver of Lumerical. So it solves the Maxwell equations, and like that, it shows how light propagates through some structures. Here you see an example of a so-called ring resonator. So you have a waveguide at the top. The light couples into the ring, and then at the other side couples into the other waveguide. So you have a certain structure, you have sources, and you have sensors, with FTTT you can simulate the propagation of light through it. Oh, so in FTDT, you can do both time and frequency domain. So the animation you have seen, it was time domain. It shows you the field as a function of time. But you can also do everything in the frequency domain by taking the Fourier transform of it. The software can show you the behavior of each individual frequency. Some frequencies do not pass to the other side. They only continue through the waveguide, and other frequencies will couple into the ring and pass over to the other side, as you can see here. Multiphysics solvers. So the FTTT solver that you've seen works with a rectangular mesh. So the whole area is divided into small squares, into small rectangles. But if you want to do multiphysics simulations, you cannot do it with that. Then you have to use a triangular mesh because you have to work with the uh, finite difference element method algorithm. So if you want to have a simulation of, for example, thermal modulators or electric modulators, you have to do it with DGTD. Next, I'm going to show you some multi-layer solvers in Lumerical. So let's suppose you have a multi-layer like a coating, maybe on a lens, for example. You can simulate that with the stack solver of Lumerical. So you could theoretically you could also do it with FTDT, but the stack solver is much faster and easier to work with in this case. So the condition is that all the individual layers must be homogeneous and must be the same in the transverse direction. So with the stack solver, you can determine the transmission and the reflection data of certain stacks that you have designed as a function of wavelength and incident angle. And this data can then be imported into SPIOS or Zemax, so you can work with it as a coating. So you can, for example, see what a windshield on a car looks like with a coating on it. Then we have RCWA, and RCWA is about the same as stack, but now in this case you can work with periodic layers. So if you have periodic structures, like here you see some unit cell that is repeated over and over again, then you can do it with RCWA. So this is an excellent tool for designing and optimizing, for example, gratings. Mode. So Lumerical has a specialized tool to simulate and determine the eigenmodes of waveguides. So let's take a look at it. So first of all, we have FDE. That is simply you design a cross section of a certain waveguide, and then the software will determine what the eigenmode looks like of a certain waveguide. So eigenmode, for those who don't know, is the shape of the light that it takes when it travels through a waveguide. And one waveguide can have multiple modes, and you can determine all of them. And also in combination, you can do this in combination with FTTT simulations. So let's say you have a design of a waveguide. With mode, you can determine what the eigenmode looks like, and then you can inject it into a structure that you have designed in FTTT. And then the software will calculate the propagation of the light. EME. So EME is is used for waveguides that are very long, but do not have the same cross section everywhere. You can see as an example this tapered waveguide. You could theoretically do it with FTTT, but because it can be a very big structure, like let's say maybe tens of micrometers. it would take a lot of time to do it with FTTT. In this case, it is better to use EME. And EME also works bidirectional, so it determines not only the propagation in one direction, but also in the other one. And as you can see, it slices the whole waveguide in certain areas. Here, suppose we have a design like this. In this case, you can see that the cross section here is uniform. So we only need one section here. So the other side is divided into many smaller sections. But because here it stays uniform, we can just keep it in one unit in one section. So an example of EME is for example fiber coupling into a waveguide. So here we have a fiber, and then we have a micro lens, and the micro lens couples the light into this edge coupler here, which is a tapered waveguide, and then the light continues to a uniform waveguide, as you can see here. Yeah, so let me just show you how this works. First, the light starts in a fiber. So with Ansys mode, with FDE, you can determine the eigenmode of the light. And then you can import those data that you found here into Ansys Optic Studio, into Zemax, in order to simulate the propagation of the light through the lens itself. And then with FTTT, you can simulate the propagation of the light from the lens to the coupler itself. And then we go again to Ansys mode, but this time to EME. And then we can simulate the propagation of the light through the edge coupler, through the tapered waveguide. And then with all of this, we can determine the coupling efficiency from the fiber into the waveguide. FEEM or FEEM is also an eigenmode solver. But as you can see here, in this case, we use a triangular mesh. And this is for the finite element method. And as you can already guess, we do this because sometimes we work with multiphysics. Suppose we have an thermal or an electric modulator, then we can use FEEM for it. So when heat or chargers are involved in your simulation, it is best to use FEEM. Oh, and also for waveguides with gradient index through the cross section. Interconnect. Interconnect is a simulator of photonic integrated circuits. So suppose you have a whole circuit of different photonic components. You cannot make an FTTT simulation through all of this. That would take too much time. So instead, this whole circuit is just defined by certain components. Here you have a design with some ring resonators in it. You see that all these ring resonators are just replaced by blocks. And here you have waveguide couplers, and here another one, and those are here and here. Now let's go back. So in interconnect, in FTTT, you can design the individual components. So let's say in FTTT, you do a simulation of one of these ring resonators, and then you can import the data that you get. You can import it into interconnect, and then you can see how this component that you just designed interacts with other components in the photonic integrated circuit. What you can also do is you can use interconnect to split up one component into smaller parts. And the reason why you would do this is because a simulation like this, even though it's a little bit less accurate, is much faster than doing a simulation like that. The reason for that is that when you do an FTTT simulation of a ring resonator, the light is trapped inside the ring, and because of this, the simulation will continue for a long time, and it takes a lot of time to calculate this. because of that, sometimes it is preferred to just do it like this in interconnect. So now that I've shown you some of the modules in Lumerical, I will show you how to design a crow filter. A crow filter is the same as a ring resonator, but it consists of multiple rings. And the reason for that is that the filtered, so a ring resonator works as a filter, and the filtered bandwidth gets smaller the more rings you use in your design. So first what we are going to do is with Ansys mode, we are going to determine the eigenmode of our waveguide that we're going to use. In interconnect, we are going to determine the coupling coefficients that we need for our rings. And with interconnect, again, we are going to tune the filter. So we are going to shift the resonance frequency. And then with FTDT, we are going to determine the gap distance between the waveguides in order to get the wanted results. So this is what a crow filter looks like. Light comes in, and most of the light just passes through this waveguide through the through gate. But specific frequencies will couple into these rings and will be filtered out and go through the drop gate like this. So we could do an FTDT simulation, but as I told you before, it would take too much time because we have to sweep along different parameters. So instead, we just choose to do it in interconnect. So first of all, with Lumerical mode, we determine the eigenmode. We are going to use the first eigenmode of the waveguide. And there we can see what the effective index is of this eigenmode. You can also determine things like losses, like the loss of light per centimeter, and also band losses can be determined with FDE. We want to have a free spectral range of 79.5 gigahertz. The free spectral range is the distance between two different resonance frequencies, so the frequencies that get filtered out. The free spectral range is equal to the following equations: the speed of light divided by the group index times 2 pi times the radius of the ring. We see the group index here, and we see that there is also that it's a complex number, but the imaginary part is very small, so we are going to ignore this. We just take a real part, it's 3.89. We fill it into this formula, and with this we find out that the radius of the rings should be 154 micrometers. 154 micrometers is a very large radius, so we are going to assume that there are no band losses in our design. Yeah, so next what we are going to do is we are going to determine the coupling coefficients, so K1 and K2. So K1 is the fraction of the light that jumps from this waveguide to this waveguide, and also from this waveguide to this waveguide. And K2 is the coupling coefficient between the two rings. So we are going to do a sweep along different wavelengths, and then we see the gain through the through gate and through the drop gate. As you can see here, the blue curve is the through gate and the other one is the drop gate. And with this information, it is given in decibel, but if we convert it, then we find that the following values are K1 and K2. So next what we are going to do is we are going to apply a voltage to the ring resonator, because if you apply a voltage, the resonance frequency will shift. So we do a sweep along different voltages, And in order to get a wavelength of 1550, which is what we want, we have to apply a voltage of 0.95 volts. Next, what we are going to do is we are going to determine the gap distance between the rings, between the waveguides. We do it both for the bend-to-bend waveguides and from the bend to the straight waveguides. So what we do is we make a model of these waveguides in FDDT, and then we do a sweep along different gap distances. And like this, we find out, we know the coupling coefficients K1 and K2. And like this, we find out that the gap distance should be 410 and 630. And so with all of this, we have designed our waveguide. So we have designed our Crow filter. And I will continue to the next example, designing meta lenses. So first of all, what is a meta lens? A normal lens. So first I'm going to show you what a normal lens is. A normal lens just uses refraction to focus a beam of light. This is the ideal case, of course. This is what we want, but in real life, this is, wait, sorry. Sorry, there's something went wrong. So meta lenses uses, so normal lens uses refraction to focus light, but the meta lens uses phase modulation to focus light. And I'm going to show you what I mean by that. So this is what a meta lens looks like. It is an array of rods with different diameters. And why do they have different diameters? That is because, yeah, I'm going to show it here. So on the left side, you have a small rod, and on the right side, you have a bigger rod. And as you can see, the light moves faster through the small rod than through the thicker rod. And because of this, the wavefront gets shifted a bit to the right, as you can see. And after the light has left those rods, the light will now move a little bit to the right. If you put all those rods into a grid like this, then the light at the edges will move faster than the lights at the center. And because of this, the wavefront now gets shaped like this. It gets curved, and the light will focus after it has left the waveguides. So why would we use meta lenses? Normally, light gets, so this is an ideal lens. All the light gets focused onto one point, but in real life, it looks more like this. The light is not perfectly focused, and the lens is a little bit aberrated. And the type of aberration that you can see here is called a spherical aberration. And meta lenses do not have spherical aberrations because there is no curvature at the edge. Another good thing of meta lenses is that they are very thin, and that means that they can be used in spaces where there's not much space to work in. First of all, we are going to define a target phase. So we are going to, our meta lens is going to mimic a spherical lens like this, which means that it should have a phase profile that looks like that follows the following formula. So here's lambda is the wavelength and f is the focal length. So this is the formula that we work with. And now that we know what our phase profile looks like, what we need to do is we need to determine the radiuses of the rods as a function of position. So what we first do in RCWA, we are going to do a simulation of individual nanorods. So we do this for different radiuses of the rods and different heights. So we have done it here, as you can see it. And then we are going to fix the height of the rods at 1.3 microns. And so we have here the transmission of the of the nanorods, which is almost constant. And here we have the phase shift as a function of rod radius. So next we are going to place some of those nanorods in a grid, as you can see here. So each number here corresponds to a certain nanorod with a certain amplitude and phase. And next what we can do is import those data into Optic Studio, so we can do ray tracing with this meta lens that we designed. So as you can see, the direction of the light depends on the local phase gradient, so dp over dx and dp over dy. And when we look at the spot diagram, we see that there's a little bit of a plus shape in it, and that makes sense because the grids are placed in a rectangular. The rods are placed in a rectangular grid, so that's why it looks like this. So those were some two examples of what you can do with Lumerical. So we will wrap up, and I will pass the word to Tisa.
Thank you, Kim. I hope everyone enjoyed this session. But before we say goodbye, I would just like to inform you about our training options. If you can move to the next slide, please. So in case you want to learn in practice how to use Ansys Lumerical or any other Ansys tool, we offer different training options. You have upcoming trainings listed on our website. Those trainings already have a set date and the location. If you don't find a training on the website that would meet your desires, then we also offer trainings on request. So you fill out the forum and then we organize something that suits you. And the last option is Ansys Learning Hub. Those trainings are all online, so you can learn in your own pace and whenever you want. But although the trainings are free, you need the access to the Ansys Learning Hub. So if you don't have an access, you can contact me and we can talk further how to provide it to you. And that was everything from my side as well. So I wish you all a great day ahead, and thanks again for joining the webinar today. Thank you. Bye.